Hello, and welcome back to the second episode of the Nintendo Entertainment System development series, where we develop an emulator from scratch. So in the first episode, we did a humble beginning of setting up a SIG project, and let's see. So we set up a basic SIG project, and then we did a very simple, fetch, decode, execute loop where we fetch the next byte from the program counter. We decode it basically, so we switch over the opcode and we execute the opcode, and we already implemented one opcode, which is the absolute jump, which was the 4C byte. So yeah, today I thought we take a look at this NES test that I found. Opened up on the wrong monitor. Okay. So I thought we take a look at this NES test that essentially. Let me turn down the music here from myself. That essentially tests different instructions. So apparently it comes with a binary file and with a log file, and then the log file tells you what the CPU should look like after each instruction. So if I copy the link, and I already made a directory here, tests, where I want to copy this into. So if we just go into tests and download the NES file and also the log file. Okay. Then we see that we have this log file, and this I already got some VS Code extension that allows me to inspect binary files with some sort of hex view. So we see that this is a NES ROM file, and we see it starts apparently with the magic number NES, and then it also has some strings, run all tests, branch tests, flags, something like this. And apparently what I saw is that the tests started this address, and I already googled a little bit before, but how to load ROM in NES. I saw that, if you click on any link, I already saw this thing that, okay, it has a header, and then, where is it? It has a 16-byte header, and then the ROM is either 16 or 32 kilobytes big. And if it's 16 kilobytes big, you should mirror it into these two, and if it's 32, it should be this. And we see that it's 28. Maybe that's kilobytes and not kilobytes. I'm not sure. But I think it should be fine that we skip the header, and then we load it into this address space. So let's go. So what I'm thinking is, last time we just set up a memory array for the entire addressable space of 65,536, and we just set the first 3 memory addresses, and then basically we executed the first kind of line here, which was a jump to this address, and the program jumped and then of course this address F5 C5 which is little endian, yeah, so this address C5 F5, if you jump to this address it's 0, and then the next one it didn't know what opcode 0 is and the program ended, but this is where we are right now. So what can we do? I thought we can what is there? Open absolute. Okay, let's just open it in an absolute path here. I mean, this doesn't have to be pretty, this is just our little test thing, so we can test things. Okay, flags. Let's see. How does this work? Access subpaths. No, that's open dir. Open file absolute. Okay. Mode. Read only. Okay, that sounds good. And const run file equals, this is probably, yeah, so if it's an error we report the error back, and otherwise we open the file, and then read. Okay, and we can give it the buffer. So can we seek by 16 bytes, and then read into the buffer. Okay. So this would read the ROM into the buffer, but what we want to do is to map it, and we could write some function that adds or whatever, but I'm thinking we can just offset this. So instead of passing the pointer to the memory, we can pass a slice that starts at this address. So basically, starting from this address, it would seek the file by 16 bytes, and then it would load the file content into this. Can also close this file. Close. Okay. All right. Let's see if this works. Seek can also fail. Okay, let's just try. And read can also fail. Okay, so try. Use size value ignored. Okay, so this I assume will return the size of what it read, but in this case we don't care because we know that the file is small enough that it should fit, I think, and if not, and it crashes, it doesn't matter. Okay. Okay, so this is the memory. Nice, and we can see that it's 0, and then oh, that takes a while. Can I go down here somehow? Can I jump to something? Hello? That's a really good interface. Ah, nice. 32, whatever. So we can see that that still takes a while. Okay. Come on. Why can't I jump to an address? Yes, there it is. So the file starts with 60, 78, blah blah blah. And is that what we expect? Let's see. We open this in hex. Don't know what I did here, but let's see. Yeah. So it starts with, it starts here. It starts with 4C, F5, and so on. This is 4C. Yeah, so this is 1 byte, 2, 3, 4, 5. Wait, this is... I don't get it exactly, shouldn't it? 4C, it starts with 4C. But that's the first instruction, 4C, F5. Okay. Nice. Perfect. Okay, so we see that here 4C, F5, C5, it basically starts with the first instruction, jump. So let's see if it actually jumps. That would be very cool. Let's run it again. Oh, I didn't set the PC. Okay. PC equals, let's copy it from here. Okay, so we map the file into it, we set the PC, and then let's see. What am I looking at? Okay. So I think it did the jump. I'm just very bad at printing stuff. I should definitely print the CPU before the instruction. So kind of CPU before instruction. And then, yeah, that's fine. Okay. And then opcode not implemented. I would expect it to do at least one opcode. Did I do something wrong? So should this be I don't know if this should be this or this. I think this is fine. But this is 8. And then let's just guess, whatever. So it should start immediately. But that would be at 8. No, wait, what? If the program is 16, it's mirrored, meaning it's and. Okay. So I think what I should be doing is just. Does it work if I just put it in here? I don't want to mirror stuff right now. And this should just be this. Yes, there we go. So before the instruction, it would be very beneficial if we print the, let's print the actual thing. So okay. So this is a CPU dot x, CPU dot y, CPU dot p, and CPU dot sp. And now is the question how to print this in hex. Maybe like this? I have no idea. No field named P. Wait, what did I do? Stack pointer. Okay. So program counter. Let me just CPU dot program counter a xy PCSP. No, now I print the program counter twice. Let's print it here. Let's see. Just format. Absolute cool. Look at this. Second episode and we're kind of doing something. So at first, this is wrong by the way, because what did I say? PC, oh my god. AXY SP. Okay. Okay, look at this. The program counter starts off as C0 and everything else is 0, and then it should jump to C5 F5, which it says here, jump to C5 F5. So in the next instruction it's at C5 F5, and then it says opcode not implemented. And maybe I should say here standard log.error unimplemented opcode. And this should also be hex. Unimplemented code A2. Now this is 5F5 from where we were. So if we jump to 5F5, then we see it's A2. So it actually jumped 5F5 from the starting point, and now it read E2, and it threw up his hands and said, okay, bro, I don't know what this A2 business is, but it's not part of my switch case, so I'm giving up. And that's where we are. So I think it would be a very good strategy to just implement the opcodes just in this random order that they appear in this test file, and then maybe we can just, you know, run more and more of the test file. So let's see. So this is done. This codes. Just looking for some sort of, yeah, we were on this side before. Arithmetic shift and branch, blah, 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 blah. Okay. So the next instruction apparently is A2. A2. So, okay. What is A2? A2 is load immediate. Load X loads a memory value into the X register, and A2 is immediate. Okay, so it basically takes the, let's see the log. Load X immediate, and it loads 0 into X, okay. So it should stay 0, I suppose. Ah, and this is the circle count, this is also very cool. P24. P is the flags, probably. Let's worry about the flags later. So it loads. Do we have another A2? A2. Or we can also look for load X. Okay, so it is load X. So here we load the immediate value of 40, and we see that on this line here, X is 0, and then after we load X, everything stays the same, but except for the counters and such, but X becomes 40. So this is load X. So let's call this immediate, I suppose. 0 page, page, absolute. Okay. Should be fine. Is there also load y? Load y. Load y immediate is A0. Okay, let's just implement both if they are so similar. And this should be here. All right. Very cool. So we had fetch byte, but fetch byte, it occurred to me that it fetches the byte at the PC register, and then it increments the PC register. We probably want the helper, but we don't want it. I mean, this is fetch in the sense of fetch from PC, but we need some sort of helper to read the next value. Actually, it is the next value, isn't it? So, oh, so it is the same, actually. So I think CPU.x CPU.y, and I did it the wrong way around. Okay. Yeah, this may work. Let's see. Fetch 2 bytes. Expected type U8, found U16. Oh, I said fetch 2 bytes. Fetch byte. Cool. We are further along. Will you look at this? So now we are here, and we're loading 0 into X, which is very cool. That means nothing happens. And then we are here, and we say 86 unimplemented. 86 in hex, yeah. So this would be here. Let's see, 86. STX stores the X register value into memory. It stores the X register into memory. And 0 page. Okay, this has 0 page Y. That means probably plus Y and absolute. STX 0 page. Okay. STX 0 page. STY 0 page. Let's just do one. STX 0 page. See also LDX Yeah, but what does 0 page mean? 0 page. Okay, addressing mode. Yes, STX 0 page. Addressing mode, 0 page index. Index. Indexed addressing mode uses the X and Y register to help determine the address. Okay. So 0 page index means the argument plus X and then modular 256. Okay. And okay. Absolute index, indirect index. Okay, that makes sense. So 0 page, what that means is that we store we store 0. So this is the pointer, 0 page. So we store it into 0 because there's no offset. And no, the offset is X. Oh yeah, these two kind of come together. So first you set X to 0. So you say, okay, from the 0 page I want 0 offset. So which you set this here. And then you just tell it what to store immediately, I suppose. So you store the value of X. No, the other way around. So you tell it an address and you store the value of X into it. Is that correct? These are always so, like, stores the X register value into memory. Okay. So, but into this memory. But this is 0 paged, which means, okay, let's just look at a different STX. So this this reads. Oh, this is a different STX. We need the we need the 86. Okay. Come on. Six. 86. Okay, so we store 55 because X is 50. This is the offset of the 0 page, I think. And this should be the value of x, but x is 46. I'm very confused. Okay, and it only appears here. Let me see. Okay, AI, what do you have to say? The current value of x. Okay, let's implement it like this. So we just take the value of x and we write it into memory, which means also we need a new function, write byte. CPU. Actually, we don't need the CPU. Byte and address. Let's put it here. Address U16 byte. And we need the memory slice, of course. So memory at address equals byte. Memory CPU dot x. No, there should be CPU. Okay, let's just try this. And the byte. No, this should be the 0 page. Where is the 0 page? Is it 0? So we fetch a byte and can I use a U8 here? I think I need to cast it. Oh, I can? Okay. Okay. True. Not sure about this one. Okay. Let's just keep going. I think the important thing is to get some momentum in implementing these. So 20 or 2 times 16 So this is 20 jump to subroutine. It does a push PC +2 to stack, and then it does the PC to memory. Okay, jump to subroutine. Then I think we need a push. Push and pop. So this will be stack operations. So presumably when you call a function, then you have to push current state onto the stack, and then when you return from a function, or you want to use the stack, otherwise then you pop from the stack again. Push and pop. Okay, how does it work? Jump to subroutine pushes the current programming counter to the stack and then sets the programming counter to a new value. This allows code to call a function and return return subroutine or something. Return from subroutine. Okay. We also want to implement this, which is here. Return. What was it called? RTS. So this is, let's just comment this, return from subroutine. And this is jump, no. What was it called? Jump to subroutine. Okay. Okay, so pushes the current programming counter to the stack and then sets the, so I think push a, okay, no, isn't there push programming counter? Okay. Okay, so we need to do this basically, but with programming counter. We store the programming counter to the stack. The stack starts here. Okay, so when we push something, we want to say stack start equals this plus CPU stack pointer, because the stack apparently always starts at this address, and then we need to know what to push onto the stack. Push a so we actually also need, it's a little bit weird, let me do it the other way around. CPU, memory, and byte. So we want to push the byte onto the stack. So we know where the stack starts, then we set the actual memory, so write byte stack start at address stack start. What is the first write? Stack start byte memory. Yes. So we write this byte, and then we need to tell the stack pointer to point to the next free location, which means we decrement the stack pointer because the stack grows towards 0 or like into the negative direction. And when we push from the stack, when we push to the stack, it's called pull. Okay. When we pull from the stack, we increase the stack pointer again. Yes. So SPO stack pointer plus equals 1. I think, I'm not sure, I think it can also overflow. So this operation in Zig means it can wrap around. So if you have, you have a full byte and you do +1, then it's like an error or undefined behavior if you just do plus equals 1. But if you do this, then it's defined to become 0 again. So I think this is correct. So we don't know, but let's say it's correct. So we push, that means we what did we say? We need to decrease, of course. We decrease the stack pointer and we wrap around, but the other way. If it's 0 minus 1, it becomes 1 1 1 1 again. And then that's it. And pop is the other way. So pop. Also one CPU and then memory, because it looks better to me. And this time we read byte. We don't have read byte. Okay. Read byte from memory. Memory and address 16. Return memory at address. Okay. So this is called pull. Should I also call it pull? That's kind of weird. Let's just keep pop for now. And wait, pop is the other way, so we need to first do this, then have the stack pointer, and then read byte and return the red byte. Okay. So this it here? So jump to subroutine. We push the program counter to the stack, which means we need to split up the program counter into 2 bytes. Okay, so which presumably means the okay, so the lower one should just be int. Is that truncate or cast? Truncate. Truncate, this function truncates bits. Okay. So we want to truncate the program counter. And for the higher one, we also want we want to shift, I think. CPU.program counter 8 bits. And then we can push lower and then higher. Must have known. Okay, so we want to, these should both be U8. So I think this needs a cast as well. Let's see. Expected, yes. I must admit I never know which is which. So if we have this byte, for instance, if we do, this was a bad example. This, if we do write, yeah. Then we get the higher. Okay, so this should be the higher, and this is int cast. Okay. Stack start. Yes, stack start should be U16. This is really what I like about SIG, is that the types, I mean, for some people it's annoying, it might seem annoying, and then SIG is maybe not for them, but for me, if I have to really put, you know, okay, this is a U8, so if I do something that doesn't fit into U8 but plus a U8 or whatever, so I need to say, okay, the storage is U16. I have U16 on the stack here, so I can add a U6, like 2 bytes to 1 byte, and it will still fit. I think I even need to as U16 int cast. I even need to cast this. Yes. Cool. Okay, let's wait, let me compare what we're actually doing. So we don't care about So we were here. Maybe let me just print out the line number. Let me just have Okay, I don't want to. Doesn't matter. Let's just compare it line by line. C5FE. Okay, so this. Okay, does this, then it's C5. That's so cool. These just work. FD. So it should jump to the subroutine. JSR. Jump subroutine. Okay, so because I didn't finish implementing this, so I only pushed PC to the stack. I got a little bit ahead of myself. Jump subroutine. I think I pushed it correctly. Let's see. Oh, it doesn't say what the stack. What's on top of the stack. I just see that the stack pointer from here at the beginning. At the beginning the stack is on FD and my stack is on 0. I think the stack should just be initialized with FD at the start. Okay. Looks good. And then it does the thing where it jumps subroutine to this. So we need to read 2 bytes. Subroutine address. Fetch 2 bytes, CPU, memory. And then it saves the alt PC and then CPU.pc equals subroutine address. And when we return from a subroutine, I think we need to do the opposite. We pull, okay, I really don't want to call it pull. Let's call it pull. Okay. So we pull from the stack. So we pull twice from the stack. I guess this is push byte and pull byte. I might may or may not do help us for like push 2 bytes or something, but let's just do it like this. So we pull 2 bytes, CPU memory, and I'm really not sure about the lower and higher here. Then we have to do the, where did we fetch 2 bytes? Let me do a helper here. Let's just do function combine to U16, combine 2 bytes, lower byte, higher byte. Okay, the lower, and then, no, we take the higher byte plus the lower, yes, okay. So then we can here return combine 2 bytes first, plus equals first, no, second, first. Okay. CPU.pc equals combine 2 bytes, lower, higher. Okay. I think this was not correct. I messed something up. I think this is first, second. Okay, this looks better. Oh wow, we're really plowing ahead. That's really cool. So now we are here at C7 2D, and we have the EA Sports. It's in the game instruction. Let's see. What am I doing? EA. No operation. This sounds very difficult to implement. It has no effect. It merely wastes space and CPU cycles. Alright. No. EA. So this should be map equals 0x EA. And this should be let's try to have the same order. Yeah. I guess this is fine. All right, 38, or 3 times 16 plus 8. set carry sets the carry flag to 1. This is usually done before subtracting. Clear carry flag. Okay, let's just implement these very easy flags. Clear. I'll just implement all flag things. So this is set carry flag. Let's do a little bit of this. This is 38. So it should fit in here. 38 set carry flag. Then we have I wonder if there's a way to, I mean, I suppose one way is to bring these two code paths closer together, that I don't have to scroll so far. Set carry flag cpu dot flags dot carry equals true. That's it. Clear carry flag 1.8. CLC clear carry flag. Flags dot carry equals false. Clear interrupt disable 58. Equals 0x58. Disable flag. This is after sec, so give me a sec. Set interrupt disable is 7.8. Let's just write flag everywhere because I started doing this for some reason. It's after jump absolute, and it sets the interrupt disabled flag to true. Okay. Clear decimal. CLD D8. What am I doing? Okay, we're back. I was shortly gone. So let's see. We were at CLD. This is 0x D8. And this is clear decimal flag. Hello, flag. CPU dot flags dot decimal equals false, and then set decimal flag is F8. Of course, I'm sure there's some logic to it. F8 set decimal flag. Also, there is a space missing. Z. I'm wondering if I should have just made a switch case over these and made this into a comment. I'm not sure. Whatever. I think later when you look for a bug, this is maybe easier to read, and then this is just okay. So this is the set decimal flag to true. Cool. And then there's the clear overflow flag. It's CLV. It's at B8. B8. This is after the immediate stuff. CPU.flags dot overflow equals false. All right, let me run it again. This should not be a syntax error. I don't know why I did a comma everywhere. There's another one. Don't know. Was just in the mood for commas. 83. There should be a comma here, and I think, yeah, I left it. 110. Wow. How many syntax errors can you make? B0. Branch if carry set. That sounds cool. Okay, so I think this will be the last opcode to implement in this episode. Because you cannot keep going forever. And I need to eat something. So there's more text here. If the carry flag is set, okay, branches to a nearby location by adding the branch offset to the program counter. So the offset is just red. The branch instruction, branching farther than the okay, the carry flag has different meanings depending on the context. Can be used after okay. For if page crossed. Okay, so I'm reading the instruction. This is always the thing when I'm implementing CPUs, like it reads the instruction B0. Then I presume it checks if the carry flag is set. But I think it reads the byte in any case, I would assume. Yeah, otherwise this wouldn't really make, okay, this would be really confusing if it didn't. No, it has to. So I have to read. Let me just see where it is. Okay, first interesting one. So jump address or something equals fetch byte. Three if branch is taken. Okay. 2 bytes. Yeah, it fetches 1 byte. Why can't this just be this? And then it checks if CPU flags carry is set, and if it's set, then it sets the PC to the memory. I think this is correct. Possibly correct. So at some point in the next episode, it would be cool to obviously also read in this log file and then, I don't know, parse out this stuff, and then if after each line automatically check if all the things are correct and stuff like this, obviously, but you have to start somewhere. Okay, let's see. 2F, 2F, 2F. So presumably the set. What is sec again? This is set. Sec is set carry flag. Okay, so it sets the carry flag, which is the flags here, and then okay, let me maybe do this quickly. I think you can also print the flags, but CPU.flags. But what we need to do is, right now it's just a struct. But I think if we use a packed struct that's like a byte, then we say, okay, this struct in reality is a byte. So this is, you know, the first bit, second bit, and so on. And then we can still set these things with the dot syntax, but we can also convert it to as or int from enum. No, int from, is there int from I wonder if we can just print it like this. 8, but the field has told us 6. Uh-huh. I have no idea. Zig package manager packed struct. So what I want, okay, so this is a 4-bit size. Okay. Packed struct padding. Padding. I think I just have to, okay. Was this closed? Packed struct. Padding. Okay, I think I just have to do it manually, like padding U2. Okay. Yes, so what we also need is packed struct convert to int. Bitcast packed format. This is open. Integer of a packed struct. Bitcast. Maybe this works. So where do we print it? Here. Okay. So maybe this works. Come on, Bitcast must have known result type as U8. This might be good, but we need to Google so many things. NES flags initial value. Why is the initial state of the interrupt flag? Does it say the power up, blah blah blah. Initial values after reset. Okay. FD that we set. 1, 2. What is eigen interrupt disabled? Okay. So the initial setup is interrupt disabled should be true. result equals true. Maybe we put this little thing on init reset CPU. Okay. CPU dot reset CPU. Okay. Okay. If it's in the CPU namespace, let's just call it reset. And this should be CPU. I can just do this, no? Yes. Okay, so it does something, but here the value is 24 at first. 24. 16 plus 8. So there are 2 flags at the beginning. Does this have some documentation? Not this. I clicked on the same link twice. What is this? Memory reset to rest. Emulating the CPU. Okay. So. Yes. Come on. I'm really wondering whether AI can hexadecimal means I'm really curious. I think it's joking. Continue. Zero interrupt decimal. Okay. So I think I'm gonna leave it there for this episode. We implemented a lot of instructions. I'm very sure that a lot of these instructions have bugs and are not correct yet. but I think this is still very good progress. We completely did the logic of reading in this binary file, printing out some sort of log and implementing all these instructions. And yeah, thank you so much for watching.